Now that we know a little bit about polar coordinates and equations, let's talk about how to find the derivative when we're dealing with an equation in polar form. Now remember that when we dealt with parametric curves, we were able to get our derivative dy dx by taking dy dt and dividing by dx dt, where t was our parameter. Well, when we're dealing with polar coordinates, it's the same idea. It's just that it's theta that's our parameter. So dy dx, that'll still be the slope of the tangent line since we are graphing in the xy plane after all. That will equal dy d theta, because theta is our parameter, over dx d theta. And the question is, where do I get these? Well, we get those from these equations, knowing that x is r times cosine theta, and y is r sine theta. And we can do the derivative of each of these. So if we do that, we're going to get dx d theta equals, and I'm going to need to apply the product rule here with respect to theta. So the derivative of r would be dr d theta times cosine theta plus r times the derivative of cos, which is negative sine. And dy d theta, again the product rule, that'll be dr d theta times sine theta plus r times the derivative of sine, which is cos. And so I can put each of these expressions in my numerator and denominator here. And so we come up with dy dx being, alright, so let's apply this formula to find the slope of the tangent line to this polar graph at the point where theta is pi over 4. So we need to find our derivative applying this formula. So dy dx will equal, now we need the derivative of r with respect to theta, and that would be for this, dr d theta would be negative sine theta. So putting all these pieces together, we're going to have negative sine theta times sine theta plus r, which is our original equation, divided by so let's do a little simplifying. We're going to have negative sine squared plus cosine squared plus cosine theta divided by negative sine theta cosine theta minus sine theta cos theta minus sine theta. And these two terms here, cosine squared minus sine squared, that's the identity for cosine 2 theta plus cos theta. And in the denominator we have two of these, which is negative 2 sine theta, forgot the theta there, cos theta. And that's the identity for negative sine 2 theta minus sine theta. Now, to get the derivative at pi over 4, I'm going to plug pi over 4 into all of this. So that's going to be the cosine of 2 times pi over 4, which is pi over 2, and so on. Cosine of pi over 2 is 0. Cosine of pi over 4 is root 2 over 2, divided by sine of pi over 2 is 1, so that's negative 1 minus root 2 over 2. And we can multiply top and bottom by 2 just to make this look a little bit more friendly. And I'm also going to transfer the negative to the top. And if I type that into the calculator, that's approximately negative 0.414. Alright, so let's use our calculator to verify this answer. 1 plus cos theta gets entered. Got my window dimensions, 0 to 2 pi. Everything looks fine there. And we get what looks like a cardioid. Let's just trace it a bit to look at some of the main points. 2, 0, when the angle is 0. Looks like it's hitting 1, 0 there, or 0, 1, which that's 0, 1, okay. And then it's going out a bit and coming back to 0, 0. Going through 0, -1, and then back. Alright. So in terms of graphing that, these are points. And then it comes out. Okay, like a heart, cardioid. And we want to test at pi over 4, the derivative, to see if it's this. So, second function, we want number 2, dy dx, at pi over 4. Alright, it's coming out to what we got when we did it analytically. The point on the graph is about there. And that looks like a negative slope and a line that's not very steep. So the next thing we want to look at is how to find the length of the arc when we're dealing with polar curves. We know how to do this with rectangular, Cartesian, and parametric curves. How do we do it with polar curves? So recall that our arc length formula when we're dealing with a smooth parametric curve is this, between t equals a and t equals b. And so what we're going to do is transform this equation in terms of r and theta. And we're going to do that by taking all of the stuff that we know about x and r and theta and its derivatives. All of this we've talked about. And we're going to apply it to this formula to create an arc length formula for polar curves. Alright, just to save us a lot of detail and time, you can show that this, taking these two expressions and squaring them and adding them together, that will equal this. And so all we're going to do to change the formula to work with polar equations is substitute this into this spot. That will also mean that this integral will now be with respect to theta, and our time A and time B will be transformed over into the equivalent angles. And so, to make a long story short, putting all that together, our equation for the length of an arc in polar form is given by this definite integral, which is equivalent to this. Okay, just one example with this. Find the arc length of this polar equation. Now you might remember that we graphed this polar equation in the last video, and you might remember what the shape of it is, because it's a common one. It was a circle with a radius of 2, centered at 2, 0. And so if we want to find the arc length of this, what we're really finding is the circumference of the circle. Alright? Now let's just trace here, just to remind ourselves that the starting angle 0 is starting at this point, 4, 0. And we graphed all this by table previously. It's when the angle is at pi when we're back to the starting point. In other words, to get the arc length, we need to take our angle between 0 and pi radians. So applying our formula, the length of our arc is going to be from 0 to pi, the square root of radius squared, which is this formula, plus the derivative of r with respect to theta. Okay, let's just do that. That would be negative 4 sine theta. So that would be plus negative 4 sine theta squared d theta. that definite integral will calculate our arc length. All right, so we could throw that in the calculator and figure it out, but I think this one's easy enough to do by hand, because if I square that out, I'm going to get 16 cosine squared plus 16 sine squared. And I'm noticing some things here. I can factor out the 16, square root of 16, which is 4. And that's going to leave me with cosine squared plus sine squared. And cos squared plus sine squared equals 1, and the square root of 1 is 1. So when I'm integrating between 0 and pi is 4. And since this is a constant, I can just think of this as 4 times pi. So there's my answer, and going back to the idea that it was a circle with a radius of 2, the circumference of a circle can be found by the formula 2 pi r, which will match the answer I got with the integral.